Okay, in this module we're going to look at the state space models. So continuing with the representation of discrete time systems, we're going to look today at state space representation or state space models. Okay. So if I have a discrete time system, that is described by nth order difference equation, we can represent this system by a set of n coupled first order difference equations. Again, nth order system, we're going to need n coupled first order difference equation. Okay, so in general, if I have an nth order single input, single output, linear time invariant discrete time system, we can represent it by the following. So in general, for an nth order single input, single output, and also this is linear time invariant system. Linear time invariant system. We can represent it by the following. X of k plus 1 is equal to a multiplied by x of k plus b multiplied by u of k, and then y of k is equal to c multiplied by x of k plus d multiplied by u of k. What are these x and a and b, c, d? First of all, x of k is equal to x1 of k, x2 of k, all the way to xn of k. And these are the state vector. This is an n by 1 state vector. And then we have the A matrix. This is an n by n constant matrix. And then we have the B. This is an n by 1 constant column vector. And then we have the C. This is a 1 by n constant row vector. And then we might have in some systems D, which is going to be 1 by 1, and this is just going to be a constant scalar. Since we have single input, single output, D, if it presents, is going to be just a scalar value. Again, U of k is the input, and y of k is our output. And again, what we listed here is for a single input, single output system. Okay, so how can we get the state space representation? An easy way to get the state space representation is from the all delay block diagram. So to obtain state space representation, we use the all delay block diagram representation. The output, and in this case the output of each delay element is defined as a state variable. Okay, so let's look at an example of a system, and we're going to get the state space representation for this system. So in this system, we're going to find the state space representation using all delay block diagram below. And the all delay block diagram, we have an input u of k, and we have a delay t, we have another delay t, and then we have b0, and we're adding these together, y of k, and we have a feedback a1 here, and we have another a0, and this is negative, negative, this is positive, and then the output is come from here, and we have a b1 here, and this comes like this and added to b0. So we have positive, positive here. Okay, so how do we generate the state space representation from this block diagram? We said we're going to come to each output of the delay element, and we're going to define it as a state. So therefore I'm going to have x1 of k here. I have another delay element. This is going to be x2 of k. Now if this is x1 of k at the output of the delay element, the input of the delay element is going to be x1 of k plus 1. If this is the output of the delay element x2 of k, the input is going to be x2 of k plus 1. Okay. Now of course I can also add the initial conditions if I want here. This is going to be x1 of 0. This is going to be x2 of 0. Okay, so therefore if I look at this graph here, I can write that x1 of k plus 1, which is this here, is equal to x2. This is equal to x2 of k. If I write x2 of k plus 1, I can see that this is equal to minus a0 multiplied by x1 of k minus a1 multiplied by x2 of k plus u of k. These, we call them the state equations. And then I can write the equation for the output. For the output equation, y of k is equal to b0 x1 b0 x1 of k plus b1 multiplied by x2 of k. Now somebody might look at this and say, okay, why did you not write y of k as equal to b1 multiplied by x1 plus k1? Why did you write it at x2 of k? And the answer is, when we write the state space representation, we write the right side of the equations have to always be in terms of x of k. I cannot come here. I cannot write this. Although it is true that y of k, I can write it. I can write y of k as equal to b1 x1 of k plus 1 plus b0 x1 of k. Is this equation correct? It is correct, but this is not valid state space representation. Does that make sense? So please keep that in mind. I have to write x1 of k plus 1, x2 of k plus 1, y of k, all of these on the left in terms of an index that is just of k. I cannot write it in terms of an index that is k plus 1. So this is not correct for writing the state space representation. I have to come here. Where is x1 of k? This is my state. This is my state. x1 of k plus 1 is not my state. It is a shifted x1 of k. x2 of k plus 1 is not my state. My states are x1 of k, x2 of k. I have to write everything in terms of x1 of k and x2 of k. And that's why I cannot write it in terms of x1 of k plus 1. Okay. Now that I wrote these, I can plot them in a matrix format. So in a matrix form, this becomes x of k plus 1, which is these two together. I can just write them as x of k plus 1. It's understood this is x1 of k plus 1, x2 of k plus 1, depending on the size. If it was a third order, it will be x3 of k plus 1. Since we have a second order, we have x1 of k plus 1, x2 of k plus 1, x of k plus 1 understood to be x1 of k plus 1 and x2 of k plus 1. This is going to equal to a 0, 1, negative a0, negative a1 multiplied by x of k. And again, this follows directly from here. This x1 of k is equal 0 x1 plus 1 multiplied by x2. And this is what I got. 0 x1 plus 1 multiplied by x2. x2 of k is negative a0 multiplied by x1, negative a1 x2 plus u of k, negative a0 x1, negative a1 x2 plus, this is 0, this is 1 multiplied by u of k. This is my A matrix, this is my B matrix. And x of 0, I can write them here, is equal to x1 of 0, x2 of 0. These are the initial conditions. The initial condition is x1 of 0, x2 of 0. Now the output is y of k is going to equal to, if I look here, equal b0, b1. So therefore b0, b1 multiplied by x of k. Again, x of k is understood. X of k is equal to x1 of k, x2 of k. And by looking at the matrix A, I know the size of x of k. This is a 2 by 2, therefore I have x1 and I have x2. This is my C matrix. What is the D? D is 0. When will I have a D? If I have a feed from the input directly to the output. Most of the system, there's not going to be that feed, therefore the D is going to be equal to a 0. Okay. So this is my state space representation. Now what we're going to look at, we're going to look at different aspects of this state space representation. We're going to look first thing at the non-uniqueness of state space representation. We're going to see that the state space representation is not unique. Any system might have any number of representation that are valid. Second, let's say next. Second, we're going to look at how to get the transfer function from state space representation. And then we're going to look at the solution of discrete time state space equation. And finally, we're going to look at the initial conditions and the observability. Okay, so let's start with the first topic, which is the non. So let's label these 1, 2, 3, and 4. So let's look at the non-uniqueness of the state space representation. Of course, this applies to discrete time systems, and it also applies to continuous time systems. So similar to how the continuous time systems, the state space representation is not unique, the state space representation for discrete time systems is also non-unique. So let's look at the state space representation and show how this representation is not unique. So if we have x of k plus 1, u of k, y of k equal to c x of k plus d multiplied by u of k, we can obtain a new representation in terms of the state vector x delta or x wiggly. We can obtain a new representation in terms of state vector x tilde of k, where x of k is equal to P matrix multiplied by x tilde of k, where P is non-singular matrix. Because we need to be able to calculate the inverse of it. This is a non-singular matrix. Okay, so let's see what happens if I came to the state vector and I said, okay, I'm going to define x of k equal to P multiplied by x tilde. Now what I'm going to do, I'm going to substitute for x of k. X of k is equal to P multiplied by x tilde. So in the equations above, x of k plus 1 is going to equal to P multiplied x tilde of k plus 1. This is going to equal to A multiplied by P multiplied x of k is going to equal to P multiplied by x tilde of k plus B multiplied by u of k. Agree? All what we've done is we substituted for x of k with P multiplied by x tilde. Now y of k is going to equal to C multiplied by x of k, but x of k is equal to P multiplied by x tilde of k. Plus D multiplied by u of k. Now I can take the first equation here, I can multiply by P inverse on both sides. So actually let me shift this. If I multiply both sides with P inverse, I'm going to get x tilde equal to P inverse multiplied by A multiplied by P multiplied by x tilde of k plus P inverse multiplied by B multiplied by u of k. Now if I look at this, these two equations, I can see that I got a new state space representation. This new state space representation, the new state space representation is that x, oh, sorry, this is k plus 1. This is equal x tilde of k plus 1. This equal x tilde of k plus 1 equal to a tilde multiplied by x tilde of k plus b tilde u of k. And then I have y of k equal to c tilde of k plus d multiplied by u of k. Again, directly by looking at these two equations, I can see that a tilde is equal to p inverse multiplied by a multiplied by p. P tilde is equal to p inverse multiplied by b. C tilde is equal to c multiplied by p. And d is equal to d. So therefore, I can write this here, where a tilde is equal to p inverse multiplied by a multiplied by p. B tilde is equal to p inverse multiplied by b. And c tilde is equal to c multiplied by p. So therefore, the state space representation is not unique. I got a new state space representation of this system by defining x of k as equal to p multiplied by x tilde. Now P, this matrix that I chose, is any arbitrary non-singular matrix. And therefore, for a given system, there's an infinite number of different state space representation. So for any given system, there is an infinite number of state space representation. Okay. Okay, so let's look next at how do we get the transfer function from state space model. So the next topic is the transfer function from state space model. So let's consider a linear time invariant single input single output system that is described by x of k plus 1 equal to a x of k plus b multiplied by u of k, and y of k is equal to c multiplied by x of k plus d multiplied by u of k. If I want to obtain a state space, to obtain the transfer function, I can take the z transform of both sides. Take the z transform of both sides. And if I do that, I'm gonna take the z transform x of k plus 1 is gonna be z multiplied by x of z minus z multiplied by x of 0, this is small letter, x of 0 equal to a multiplied by x of z plus b multiplied by u of z, and y of z is gonna equal to c multiplied by x of z plus d multiplied by u of z. X of z is the initial condition, so it's in the time domain, that's why it's a small letter. Okay, so if we set, since we're getting the transfer function, we set the initial conditions to 0. Set initial conditions to 0, and we're going to solve for x of z in terms of u of z, and solve for x of z in terms of u of z. So we're going to get z multiplied by I multiplied the identity matrix multiplied by x of z. If I move a to the other side, minus a multiplied by x of z equal to b multiplied by u of z. So all what's done, we moved this to the other side and we set the initial conditions to 0. Okay, we can write this as z multiplied by I minus a multiplied by x of z equal to b multiplied by u of z. And therefore x of z is going to equal to z multiplied by I minus a inverse multiplied by b multiplied by u of z. Okay, now we can eliminate x of z, or we can substitute for x of z in the output equation. So y of z is equal to c multiplied by x of z, but if we substitute for the value of x of z, z multiplied by I minus a inverse multiplied by b multiplied by u of z plus d multiplied by u of z. Now I can write y of z over u of z, and this is going to equal to c multiplied by z multiplied by I minus a inverse multiplied by b plus d. And this is the transfer function obtained from the state space representation. Okay. Next, we're going to look at the solution of the discrete time state space equations. Now I just want to point out, whatever we do not cover in examples, we'll cover in homework. And what I'm going to do, similar to what we've done with homework 2, I'm going to give you tips and hints on doing the homework. So it will become a good exercise and it will reinforce all these concepts that we are covering. Okay, so let's look at the solution of discrete time state space equation. So solution of discrete time state space equations. Again, if we consider a linear time invariant system, x of k plus 1 equal to a multiplied by x of k plus b multiplied by u of k, and y of k equal to c x of k plus d multiplied by u of k. And we are given u of k, the input, and we need also the initial conditions. X of 0 are known. One way we can solve for x of k, we can just recursively solve for x of k. So therefore, if I want to calculate x of 1, this is going to equal a multiplied by x of 0 plus b multiplied by u of 0. X of 0 is known, y of 0 is known. X of 2 is going to equal to a multiplied by x of 1 plus b multiplied by u of 1. But x of 1 I just calculated from in the first equation. So I can substitute a. X of 1 is a x of 0 plus b u of 0 plus b u of 1. And therefore, this is going to equal to a squared x of 0 plus a multiplied by b, u of 0 plus b multiplied by u of 1. Okay, so we can continue this recursive calculation. We can calculate x of 3 equal to a x of 2 plus b u of 2, and this is going to equal to a multiplied by a squared x of 0 plus a b u of 0 plus b u of 1 plus b multiplied by u of 2. And if I multiply the terms, I'm going to get a cube x of 0 plus a squared b u of 0 plus a multiplied by b u of 1 plus b multiplied by u of 2. If I continue this calculation, I'm going to get to x of k equal to a to the power of k x of 0 plus the summation from j equals 0 to k minus 1 a to the power of k minus 1 minus j multiplied by b multiplied by u of j. Again, a to the k multiplied by x0 plus the summation a to the k minus 1 minus j multiplied by b multiplied by u of g. Now what we're going to do is we're going to define some terms here. We're going to define phi of k equal to a to the power of k, and we're going to call this state transition matrix. And we're gonna take ak multiplied by x of 0, which is gonna equal to phi of k multiplied by x of 0, and we're gonna call this 0 input response. And you can see this is the input, this is the response of the system that is due to initial conditions when the input is 0. Similarly, we're going to take the second term, the summation from j equals 0 to k minus 1, a to k minus 1 minus j multiplied by b multiplied by u of j. And we can write this also as the summation from j equals 0 to k minus 1 phi of k minus 1 minus j multiplied by b multiplied by u of j. And what is it we're going to call this? This is the 0 state response. Which is the response of the system that is due to the input only if I set the initial conditions to 0. So some properties of phi of k. First one is that phi of 0 is equal a to 0, which is equal to identity. So one sanity check we can do when we calculate phi of k is to substitute for k with 0, we should get the identity. The second is that phi of k plus k1 plus k2 is equal a to k1 plus k2, which is going to equal to a to k1 multiplied by a to k2, which is going to equal to phi of k1 multiplied by phi of k2. Another property is that phi of negative k is equal to a to negative k, which is equal to a to k inverse, which is gonna equal to phi inverse of k. Okay. how do we calculate phi of k? Since this is essential in order to calculate the response of the system. So let's look at a method for calculating phi of k. And again, this is equal a to k. So let's suppose that the input is equal to 0. Y of k is equal to 0 for k greater than or equal to 0. Then the state space representation is going to become x of k plus 1 equal to a multiplied by x of k. Now if you take the Z transform, of both sides, I'm going to get z multiplied by x of z minus z multiplied by x of 0 equal to a multiplied by x of k. Let's solve for x of z. We're going to get z multiplied by the identity minus a multiplied by x of k, x of z, sorry. And this is going to equal to z multiplied by x of 0. So I moved a multiplied by x of k to the other side. I moved z multiplied by x of 0 to the right side. And remember, x of 0 is a small letter because this is in the time x of 0. Okay, so therefore from this I can write x of z is equal to z multiplied by zi minus a inverse multiplied by x of 0. If I multiply both sides by zi minus a inverse, I'm going to get x of z equal to z multiplied by z minus a inverse. Because I multiplied by z here, not the other. I did not write this as z multiplied by I minus a because this is just a scalar. Together, if this was a vector, I could not write this like this. But since z is just a scalar, I can do it. Okay, so therefore, if I take the inverse of z transform, we're going to get x of k equal to z inverse of z multiplied by zi. Again, you see I'm not consistent. I wrote z and I wrote it differently already. Zi minus a inverse multiplied by x of 0. But we have already showed that for u of k equal to 0, when k is greater than 0, x of k is equal to phi of k multiplied by x of 0. We showed that for u of k equal to 0, for k greater than or equal to 0, x of k was equal to phi of k multiplied by x of 0. So therefore, from here we can immediately see that phi of k must equal to z inverse of z multiplied by zi minus a inverse. Okay. Okay, let's do an example. So let's say we have a state space representation that has a equal to 0, 1, negative 1 over 6, negative 5 over 6, and the B matrix is equal to 0, 1, C is equal to 1, 0, and D is equal to 0. And we want to calculate the state transition matrix. Okay, so to calculate the state transition matrix from the formula that we have here, we're going to calculate phi of k equal to z inverse z multiplied by zi minus a inverse. And therefore, the first thing we're going to do is we're going to calculate phi of z. This is phi of k. And phi of z is equal to z multiplied by zi minus a inverse. What is this equal to? We have z multiplied by zi. Since this is a 2 by 2, I'm gonna generate z 0 0 z. This is z multiplied by the identity minus a, which is 0 1 negative 1 over 6 negative 5 over 6. And after I do the subtraction of these two matrices, I have to calculate the inverse. And after that, I multiply it by z. So what is this equal to? If I subtract them from each other, I'm going to get a z. 0 minus 1, I'm going to get negative 1. 0 minus 1 over 6, 1 over 6. Z minus negative 5 over 6 is going to become z plus 5 over 6. And this is the inverse. Now this is an easy matrix to calculate the inverse for. 2 by 2, I have to calculate the determinant, which is going to be this element multiplied by this element minus this element multiplied by this element. And therefore, the inverse is going to equal to z divided by z multiplied by z plus 5 over 6 minus, I have minus 1 multiplied by 1 over 6, but I have to multiply it by minus, so it's going to become plus 1 over 6. Now the inverse of this matrix, we're going to swap the z and z plus 5 over 6. So I'm going to get this z plus 5 over 6, and this is z. And then I'm going to multiply this negative 1 and 1 over 6 with a negative sign. This become a 1, and this negative 1 over 6. Okay, so what is this equal to? This is, if I multiply them, I'm going to get a z multiplied by z plus 5 over 6 divided by z plus 1/2 multiplied by z plus 1 over 3, and then I'm going to get z divided by z plus 1/2 divided by z plus 1 over 3, and then I'm going to get negative 1 over 6z divided by z plus 1/2 multiplied by z plus 1 over 3, and then I'm going to get z squared divided by z plus 1/2 multiplied by z plus 1 over 3. The next step is to calculate the inverse. So I need to calculate phi of k, and this is going to equal to the inverse of phi of z, and therefore I'm going to have to calculate the inverse of the matrix that I have above. How do I calculate the inverse z transform? I'm going to take this, I'm going to do the technique that we've done with partial fraction expansion. So each one of these terms that I have here, I'm going to have to do a partial fraction expansions on it. So if I do that, I can write this as negative 2z over z plus 1/2 plus 3z divided by z plus 1/3, and then I'm going to have negative 6z divided by z plus 1/2 plus 6 multiplied by z divided by z plus 1/3. I'm going to get here z divided by z plus 1/2 minus z divided by z plus 1/3. I'm going to get 3z divided by z plus 1/2 minus 2z divided by z plus 1/3. Let me expand this bracket. So what I need to do, I need to calculate the inverse of this matrix. Now, since I did the partial fraction expansion, I can easily write phi of k term by term. Negative 2z over z plus 1/2, this is going to equal negative 2 multiplied by 1/2 to k, plus 3 multiplied by negative 1/3 to k, negative 6 multiplied by 1/2 minus 1/2 to k, plus 6 multiplied by negative 1/3 to k, and here I have negative 1/2 to k minus 1/3 to k, and then I have a 3 multiplied by negative 1/2 to k minus 2 multiplied by negative 1/3 to k. And all of this is multiplied by u of k, or this is for k greater than or equal to 0. Okay, so this is our state transition matrix. Now let's say that we have an input. So continuing on this example, consider the input u of k equal to negative 1 to k multiplied by u of k. So if I apply this input and I have initial conditions x of 0 equal to 1, 0, we're going to calculate the output. So to calculate the output, we know that the output from the formula that we had in this page, this is the formula that we're going to be using to calculate our output. The output is going to be due to the input and due to the initial conditions. The 0, and we're going to have the input that is due to the 0 and the one that is due to the input of the system. Both of these together are going to give me the outputs. Oh, sorry, this is the formula altogether. Okay, so therefore, if I want to calculate the output, let me copy this. If I want to calculate the output, we can calculate x of k, and x of k is going to equal to phi of k multiplied by the initial conditions, which is 1, 0, plus the summation from k equals 0, sorry, j equals 0 to k minus 1 of phi of k minus 1 minus j multiplied by b multiplied by u of j. and therefore this is gonna equal to, we know the phi, and we can write this as phi of k multiplied by 1 0. This is the initial conditions from the summation j equals 0 to k minus 1 multiplied by phi of k minus 1 minus j multiplied by the B matrix, which is 0 1, and multiplied by the input, which is negative 1 to the power of j. Why is it? Because that's the input that is given. The input is u of k is negative 1 to k, so therefore u of j is negative 1 to j. Okay, so if I do that and I substitute for this phi of k and multiply it, matrix multiplied by the vectors, I'm gonna get, this is gonna equal to a negative 2 multiplied by negative 1/2 to the power of k plus 3 negative 1 over 3 to the k, negative 1/2 to the k, negative 1 over 3 to the k. This is the result of multiplying this matrix by 1 and 0. What is gonna survive is this term and this term, because this term and this term is going to multiply by a 0. And then we're going to have the summation from j equals 0 to k minus 1. Same thing. If I multiply that the matrix with 0 1, if I multiply this with 0 1, this term is going to survive, this term is going to survive. This term meaning this term and this term. So therefore here I'm going to have negative 6 multiplied by negative 1/2 to the power of k minus 1 minus j plus 6 multiplied by negative 1 over 3 k minus 1 minus j, and then I'm going to have a 3 multiplied by minus 1/2 k minus 1 minus j minus 2 negative 1 over 3 k minus 1 minus j, and all this is multiplied by negative 1 to j. Let me shift it. Multiplied by negative 1 to the power of j. Okay. Now we can simplify this answer, or we can leave it as is. This gives me the state transition matrix. Okay. Sorry, this gives me x of k using the state transition matrix. And of course I can calculate y of k, and y of k is gonna equal to, as the beginning of the example, is gonna equal to c multiplied by x of k, and c was equal to 1 0 multiplied by x of k. And therefore, if I multiply this with the C matrix, I'm going to get y of k equal to negative 2 multiplied by negative 1/2 to k plus 3 multiplied by negative 1 over 3 to k plus the summation j equals 0 to k minus 1 of negative 6 multiplied by minus 1/2 to k minus 1 minus j plus 6 negative 1 over 3 k minus 1 minus j multiplied by negative 1 to j. Again, in these kind of problems, I mean, you can try to simplify, or you can, it's okay to leave it in this form. And of course, for the homework or for the problems that you do, if you want to use MATLAB to simplify anything, you're more than welcome to use it. Okay, so this is my output. Of course, I can take this and try to simplify it, and it will simplify, but for the time being, we're going to leave it as this. Okay. Now the last thing we're going to discuss here is the initial conditions and the observability. So if we are given a single input, single output, discrete time system that is described by difference equation y of k plus n plus a n minus 1, y of k plus n minus 1 all the way to a0, y of k equal to bn u of k plus n all the way to b0 u of k. We said we can use state space representation to write this as k plus 1 equal to a x of k plus b multiplied by u of k, and y of k is equal to c x of k plus d multiplied by u of k. Now we're going to consider the initial conditions, the y0, and we're going to see how they're related to how the output is related to the state, the initial state vector. So if you consider the initial condition, how are y0, y of 1 all the way to y of n minus 1, how are these related to x of 0, the initial state vector? So to do that, we're going to set the input u of k to 0 for k greater than or equal to 0. So if we do that, then using the equation y of k, we're going to realize that y of 0 is going to equal to c multiplied by x of 0. Y of 1 is going to equal to c multiplied by x of 1, which is equal to c multiplied by a multiplied by x of 0. X of 1 is equal to a multiplied by x of 0. Y of 2 is going to equal to c x of 2, which is going to equal to c a multiplied by x of 1, which is going to equal to c a squared x of 0. If we continue this process, we're going to get to y of n minus 1 is equal to c a to n minus 1 multiplied by x of 0. Now we can write these in matrix format, and this is going to be y of 0, y of 1 all the way to y of n minus 1 is equal to c multiplied by a all the way to c a to n minus 1 multiplied by x1 of 0, x2 of 0, xn of 0. Now these represent the initial conditions for the difference equation. So this is my initial conditions for the difference equation. This matrix, we're going to call it Q, and this is the initial state vector that we refer to as x of 0. this Q matrix we refer to as the observability, similar to the continuous time system, observability matrix. Okay. Now if we have a single input, single output system that is described by the state space representation, then the Q matrix is an n by n matrix. And in this case, let me copy this at another page. And in this case, if the determinant of Q is not equal to 0, then we say the system is observable. And what that means, we can determine the initial state vector x of 0 by observing the output. That means we can determine the initial state vector by observing the output. For k equals 0 all the way to n minus 1. So in this case, we can take the inverse of Q since it has an inverse, and the initial state vector x of 0 is going to equal to Q inverse multiplied by y of 0, y of 1, all the way to y of n minus 1. And therefore, we are able to reconstruct the initial state vector based on observing the output of the system. Now similarly, if the determinant is equal to 0, when the determinant of Q is equal to 0, then we call the system is unobservable. And therefore, we cannot determine the initial state vector by observing the output of the system. Okay, we're going to stop here. Next, we're going to be looking at the starred transform, and we'll do that in the next module.